So as we finish up 2.4, we're going to see today how Leibniz's approach allows us to do so much more. Okay, I've told you before, Newton developed it really with a very limited scope. What was on Newton's brain when he was thinking about it? Physics. Okay, he didn't see the bigger picture that calculus affects biology, it affects chemistry, it affects economics, it affects sociology, psychology, any of the ologies. Okay, because calculus is the study of things that change. And things are always changing. And in any discipline, you can apply calculus. And Leibniz could see the potential for that. And so long-term, Leibniz has had a lot more impact. So we want to see, today we're going to talk about looking at a little bit of economics. We're going to look at a little bit of bio, a little bit just to see how things. So you need to learn the vocab. But every ology, uses its own language to all mean the same thing. So we need to talk about that. We've got the word derivative, but in physics, and when they say mean derivative, what word in physics do they use? No, they use velocity. That's what they use in physics, okay? In economics, when they mean derivative, they use a different word. So I just have to teach you the vocabulary. You already know the math, okay? You know the math. Today I just have to teach you the vocab, okay? All right, here is the physics part, all right? Physics was really on Newton. Okay, he talked about rates of change and instantaneous rates of change. This is what we think of when we think of velocity. Okay, I just need you to learn all the synonyms. Velocity, aka derivative, aka instantaneous rates of change. So, etc., all the other things that may mean. From here on out, I just need you to understand if I just say rate of change, I'm implying the word instantaneous in front of it. Okay, that goes to, it's just I'm implying that we're doing instantaneous rate of change if I just say rate of change. It's like when I say the letter X, what am I implying is in front of the letter X? A 1. We all get it that there's a number 1 there. So the implication is, if I want you to do average rate of change, I will be specific. I will say average rate of change if that's what I want you to do. But if I just say plain rate of change, I mean instantaneous. All right, so now the idea of Leibniz, okay, and his notation and how he dealt with it, okay. You learned in Ham, you did some stuff with parametrics. Do you remember that? A little bit of parametrics. In parametrics, you could do X separate from Y. You could look at how horizontal things change separately from how Y things changed. You could look at the horizontal and vertical discretely from each other, okay, discriminately from each other. That's what Leibniz allows us to do. We're going to talk about the idea of a differential as opposed to a derivative, okay? A differential is going to be synonymous to the word expected change. Okay, so now we have rate of change, but now we have expected change. And a differential allows you, the way Leibniz wrote it, to take this dx and manipulate it like any other variable. So if I put over 1 here, like that, what does that immediately trigger in your brain that you can do? Right, I can cross multiply. And when I cross multiply here, the result is that df multiplied by 1 is just df, and on the other side I have kx, and then I have times dx on the end. This is now called a differential. Instead of being called a derivative, the derivative is df over dx. When you cross multiply and split them up like that, this is now called a differential. And the differential allows you to predict an expected change, to look into the future. If I change it just this much, what impact will they have? If I tweak my vaccine just by this, what will the result be? If I impact an economic system just by this, what is the expected change to it? If I change the chemo cocktail just by this much, what is the expected result? Okay, so that's what a differential will allow us to do. He used the Greek word delta. His D was really this. Okay, that's the Greek, the lowercase delta. So he would write delta F We now have just kind of gotten lazy and turned it into df, just for our writing, but that's where it came from, the idea of delta meaning the idea of change. Okay? All right, so here, vocab. Let's just do a geometry question. From geometry, we know that the area is pi r squared of a circle. So find the rate of change. So if I'm asking you for rate of change, what am I asking for? I'm asking for the instantaneous rate of change, which is the derivative. And so when I want the rate of change, you'll have dA over, what else is changing besides the area? R, the radius. Does pi ever change? No. Okay, so the things that are changing are dA over dr. We could say that this is the derivative of the area with respect to the radius. Knowing that pi never changes. So if pi never changes, what kind of a number is it? It is a constant. And what do we do with all constants, like 2s and 5s and 11s? They just sit there. They stay there as a constant. Okay, that was what Sean was like figuring out, right? That 2g, its derivative is 2g prime. The constant stays there. So pi is going to stay there. But then what do I do with the other parts? Well, what rule do I need to apply for the square? Power rule, okay? I need to pull it where? To the front, okay? So I'm going to pull that 2 to the front. And then what do I have left? R to the what power? 1. Have you ever seen 2 pi r before? What's 2 pi r? Circumference. The derivative of the area is the circumference. Right, I know, it's a little bit mind-blowing. All right, because how many dimensions is area? No, that's volume. How many dimensions is area? 2 dimensions. How many dimensions is a circumference? It's like a string, right? 1 dimension. I wonder if derivatives have anything to do with dimensions. They do. Okay, we're going to start talking about it. All right. Now, evaluate the rate of change when r is 4. Okay, so if we're actually evaluating it, and it says the rate of change, so then we just have to plug in the number 4. 2 pi times 4, so that'll just be 8 pi. Don't worry about getting me a decimal. I love 8 pi. I really don't want you to tell me, 25 point whatever. I like 8 pi. Now, find the expected change in A. So the expected is now, all right, you kind of have to go back to your derivative and think, I would cross multiply. I'm going to drop a 1 under here and cross multiply. Really, what's the result when that happens? When I would cross multiply? dA is going to be by itself, right? Because dA is going to be multiplied by what? 1. All right, so the expected change will be dA by itself, and then the 2 pi r is going to be multiplied by dr. Okay, find the expected change in A if r is changed by 0.05. So where does the 0.5 go? Is it going for r? Is the radius 0.5? Or is the radius being changed by 0.5? Changed by. And the word change in Greek means delta. And so where am I going to put the 0.5? For the delta r, or the dr. So this would be the expected change in A is 2 pi times the radius of 4, which we just had from the previous part, now times the 0.5 given. And so the expected change, okay, turns out to be 4 pi. The expected change in what? In the area. So that means if I change my radius by 0.5, so if I make my radius 0.5 bigger, 0.5 centimeters, 0.5 inches, 0.5 meters, whatever, if I change my radius by 0.5, I will expect my area to change by 4 pi, which is over 12 units. Okay, I mean, that's kind of amazing, right? If you change radius by half a unit, the result is that the area is changed by over 12 units. That's a lot. That's a lot of change. So you got to think little bits of change are very powerful in the big scheme of things. Just you don't want to change something a lot because that could have a huge impact. Small change nets large expected change. Yeah.
Would we have to prove that? So it's and then we have to.
No, Leibniz already proved it.
All right, cool.
Okay.
Thank you.
Okay, great. All right. Other sciences, other ologies use the expected change. They call that sensitivity. But it's the same word. It's the same expected change. So now we have a new word in sensitivity. Okay, anybody, any allergy sufferers here? A couple, maybe. What are you allergic to? Dust mites, okay. Say that again. All fur and feathers, nice, okay. If you're like a pollen or a ragweed or whatever, you're like, I am really sensitive to that. A small change in the pollen count can have a huge effect on your allergies. Okay, you are very sensitive to that. And so when we use sensitive, that's the idea of expected change as well. Okay, so I just need you to understand that new vocabulary if that's what they're asking for. Okay, all right. So for example, we don't live in an agrarian society, an agricultural society here in our particular area, but you don't have to go far in California. You drive through the middle of California up Highway 99 and there's, lettuce and everything growing on either sides. So we don't do it, but let's talk about that in terms of the agriculture science. If a rainfall has been low, a small increase, we just need a ½ inch of rainfall. What is the expected change that would have on the crops? All right, and so if you take a derivative like this, C standing for crops and R standing for rainfall, if you cross multiply, you'll get DC by itself being K, which is a constant, times R times dr. So then the scientists, the agrarian, agricultural scientist people can take, if we expect a predicted rainfall, the change in rainfall to be blank, we can expect a change in our crops to be blank, and they can figure that out, okay? It's sensitive to the weather. Okay, if you are a chemist and you're working in a lab and you're trying to develop a new drug, and your drug formula is set up this way, do you want to know if I change the person's dosage by this many milligrams, what can the expected change in their temperature be? So again, now this is already set up to do a cross multiply. This is a little different because when we cross multiply this time, what happens to the dt? Yeah, we get an x there, and on the other side we have k dx, and we really don't want that x there. We want our dt to be by itself so we can figure out the expected change. We want to get that all alone, so we just have to redivide by the x so that we end up with the expected change in the temperature will be k divided by x and then times the dx. And so you would use the formula. K would be a constant that the scientists would have determined from their lab research. X would be the amount that they're currently taking of the drug. Dx is the amount you're going to change the drug. Okay, so X is what they're already taking. Dx is what you want to change it to. Or maybe it's a chemo or something. Are you going to make that change? Are you going to make go up? Then your dx would be positive. If you want to lower the dosage, then you'll have it be negative, so that goes down. Yeah.
Why doesn't k divided by x?
Why? Well, it's the whole thing.
Oh, okay.
I mean, I could write it like that if I wanted. It's multiplication. All right. Derivatives in economics. Okay. Those guys, I wish they'd all just get together, but these people call it marginals. Okay. But if something changes marginally, it doesn't change very much. It's a tiny bit of change. I'm just going to change it, a marginal change in economics as opposed to a major change in economics. But it's still, this thing is a synonym. It still means derivative or rate of change or sensitivity or expected change. It's all the same thing. So the feds, if they're looking to change the interest rate, well, if we change the interest rate by this, what is the expected outcome on the economy? If we tweak this, if we set the interest rates to be such a, we're going to raise them, What's the expected change on the economy? Are we going to lower the interest rates? What's the expected change? It's all math. They're all doing it, okay, behind the scenes. Okay, the marginal cost. If I change my price, either higher or lower, but if I change it, what's the expected result of the amount of people who will buy it? Okay, if I lower my price, I'm hoping maybe more people will buy it. But they're paying a lower price, so I'm going to earn less in the long run. If I raise my price, what's my expected change to my bottom line for my company? All right, so let's do a real example, okay? We need washing machines, so somebody's got to make them. So suppose you're working for a company that's designing, and I have a new washing machine. I have my old one for 25 years. I got a new one, love it. All right, but suppose that we need to understand what all of these things mean. Okay, so that's my job, is to teach you that. All right, C stands for cost, X stands for washing machines. So you tell me what C100 means. Okay, anybody? Okay, C100 is the cost of producing 100 machines. All right, the next symbol, I don't know if any of you have ever seen that before. Has anybody seen that symbol before? Seen it?
I mean, not on like a variable, but like when it's like 3.3 to infinity. That's what you said.
Like repeating? Yeah, this means something different. This is an economic. It does, yeah. We call it C bar, and it is the mean, comma, average. Okay, C bar. Got T bar over here. All right. So C100 is the average or mean cost of producing 100 machines. And we get it in a per machine cost. All right, so if C100 is the total cost of producing 100 machines, and C bar is supposed to be the average mean cost of producing each machine individually, okay, all 100 machines, but what would it be for each machine? Okay, what's the math on that? How do you figure that out? You take C of 100 and divide it by 100, almost. If you only do that, you'll get it wrong, okay? The correct way to do that is to take C of 100 minus C of 0 over 100 minus 0. Okay, the correct way to evaluate mean is to take the total minus the startup cost. Okay, you have to subtract the startup cost, which is the cost of producing no machines. How could there be costs in producing no machines? What does a company have to pay for before they've even made one thing? Okay, maybe there's licensing. What else? You got to buy the machine. You got to buy the machines that are going to make the machines, right? What else? You need a place to do it. You get a building or a warehouse. Okay, you got to sign a lease and you have rent. You got to pay for insurance for your people who are working. Okay, I mean, right? Startup costs. You have to include that. All right. Okay. Then we have C prime of 100. Okay, we call this the marginal cost, also known as the expected cost. And it's the expected cost of making one more. Just one more. If I could make just one more. Okay, well, what in this scenario, what would be one more machine? The 101st machine. Okay, what would it be? What's the expected cost? Assuming I've already made 100, what would the expected cost be to me if I would make one more, or the 101st machine? I don't have to actually do it. I'm just predicting what it would be expected to be if I did. So business people use this all the time to predict if it's worth it to make the next one, to make one more. But the assumption is you've already made the number here. So the 100 is a past number. Assuming I've already made 100, what would be my expected / marginal cost if I just made one more? You can do this to profit. That would be P prime. P prime would be, what would be my expected profit or my marginal profit if I just made one more? All right, those are the vocabs. Your questions over the weekend are going to just throw different ways of asking you questions. The math is always the same. It's just a different way of asking about it every single time. So that was my goal, for you to walk out of here feeling more literate in reading those kinds of questions.